All right. How I did some of the homework, if you've looked at it, is give a expression in the form of a summation of, say, 0, 3, 5, 6, 8, 10, 11, 12. Let's just say that. Now, we're going to be using, the idea is to use a K-map, get a little practice with that, to find the Boolean expression for this. So, draw 4x4 K-map. Let's see, this is f of w, x, y, z. W, x, y, z. Uh, 0, 1, 1, 1, 0, 0, 0, 0, 1. And this will be W, X, Y, and Z. All right, so 0, 0, 0 in binary is 4 zeros. That's going to be a 1. 3 in binary is 0, 0, 1, 1. 5 is 0, 1, 0, 1. And 6 is 0, 1, 1, 0. This is turning out to be a little bit, okay, 8 is 1, 0, 1, 0, 0, 0. And 10 is 1, 0, 1, 0. And 12 is 1, 1, 0, 0. Let's make this one a don't care. And we'll fill in the rest with zeros. And don't care and equals, what's that, 2? Okay. So now that we have the K-mat drawn out, we can do our grouping with the corners. The don't care in this one, don't care in this one, and these two, and this one is flying solo. All right. So the expression is going to be start with the 4 corners. That's going to be in Z prime and X prime. Y and W don't matter, so F equals X prime, Z prime. Then let's do that's in W, that's in Y prime and Z prime. This one is going to be in W prime, Y, and Z prime. And finally, the solo one is going to be in W prime, X, Y prime, Z. So W prime, X, Y prime, Z. Okay, so you have the reduced expression. Now you can do a NAND implementation of it. So you have your first term, X prime, Z prime, going to go to a NAND gate. Like so. And your next one is going to be the three literal term, W, Y prime, Z prime. Go to a 3-input NAND gate. W prime, Y, Z prime. Another 3-input NAND gate, which they do make them. And finally a 4-input NAND gate. W prime, X, Y prime, Z. And then finally to the output. So that is the NAND implementation of that function described by the summation of those terms. I see some people still writing. I'll let people catch up and all that. But now a three. Last time we did what showed how to do a 3-input NAND gate. So you can if you feel like drawing out the 3-input and the 4-input NAND gates, you can, or you could just use the 3 and 4 input varieties as one symbol. Let's see here. Everybody caught up on this? Okay. And this is how you would do like 3 or 4 of the problems on the homework. This type of setup. Remember, if it's the pi symbol here, these numbers represent the zeros in the K-map, but not the ones. So there is one that has the pi symbol, the product symbol, for that expression. We're all good? Okay. Here. Now we're going to get into, like I mentioned last time, circuits with multiple inputs and multiple outputs. One of the more common ones is called a decoder, where it takes as an input a binary number and then asserts high on one of the multiple outputs. We'll do a 1 to 8, no, I'm sorry, 3 to 8 decoder. The idea is you have 3 input lines, S0, S1, S2, and you're going to need these to be inverted as well, an inversion. And then you're going to have 8 outputs. You're going to have 8 outputs. So the outputs are going to be representing one of the 8 combinations of the 3-bit input. So this is going to be 0, 1, 2, 3, 4, 5, 6, and 7. Now in binary, those are the 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So, what combination of inputs here makes 0 high? Let's go ahead and we'll get to that in a little bit. All right, so in order to have your all zeros high, you need to have all 3 inputs 0 and then inverted and go into an AND gate. So you have have them go like so into an AND gate. So if all three are low, it inverts all of them and goes to an AND gate and asserts that high. 0, 0, 1 is going to be another AND gate with 0, 0, and 1. And then 0, 1, 0 is going to be yet another AND gate. 0 from the first input, 1 from the second input, and 0 from the third input. 0, 1, 1. 0, 1, and 1. And then 1, 0, 0. 0 here, and 0 here. And then 1, 0, 1. Yeah, 1. Wait a minute. Yeah. 0 and 1. And then keep on going down. 1, 1, and 0. And then finally all ones. 1, 1, and 1. So it's just a lattice of crisscrossing wires. Each AND gate is a basically a selector for a particular combination of inputs. Each input has a unique output line. So you can, as you count up in binary on the input lines, one of the 8 will turn on. So yeah. Now where this is sometimes used is a chip that has multiple inputs but just one output. You have what's called a multiplexer. And I believe we covered the data selector earlier on, using an AND gate as a data selector. Well, this would be, go to an AND gate. Each one. And you would have your inputs, I0, I1, I2, I3, I4, I5, I6. Did I miss one? Yeah, okay, I got it. No, I7, and in this way, you can, and then feed these all into a big OR gate. And this way, you select which input you want to have come out. You select you give the binary number of the channel that you want to go through to the output, and the decoder will choose which unique line will go to the output. And so this is a 8-to-1 multiplexer. Sometimes referred to as a MUX. But the decoder is used to select the line in the that goes to the output. So you get You can select in a computer which line, which operation goes to the output. These are frequently used in ALUs, arithmetic logic units, where you have your arguments come in and all the calculations, addition, subtraction, multiplication, etc., and, or, exclusive, or, whatever, come in, and the function is for the output is selected by giving it a binary number. All of them get calculated, but only one of them gets selected to go to the output. So you get more into this in computer org, in the logic section of that course, if you're computer or electrical engineering. But yeah, it's a very commonly used chip. The decoder, let's see here, is typically drawn on a schematic like so, and the multiplexer is a trapezoid going the opposite direction, where you have your 3 select inputs. And 8 inputs this way. So you have S0, S1, S2, I0, I1, I2. And then U0. You'll frequently see on schematics and data sheets the use of the letter Q for an output. The reason for that is fairly simple. Instead of using an O for output, that which can be confused as the binary number 0, they use the Q, which looks like an O, but it's the output. So that's one thing that you might get used to seeing, is the Q is used as the output. So I've been writing out on state tables and that sort of thing for the output. But now the state tables for these two things, everybody got the schematic down? Okay. I'll do a state diagram, or a state table. the state table for the 3 to 8 decoder, you have S0, S1, S2, and you have your output, and you have no, that's 0, 1, and your output is Q 0, Q 1, Q 2, output high. Okay. Now the multiplexer, this is the decoder. The multiplexer have S0, S1, S2, and then you have I7, 7, I6. Alright. You can skip the I's and the I columns. Q follows I0, I1, I2, I3, I4, I5, I6, and I7. So that's the multiplexer. So the let's say here, when you have 101 on your select inputs, I5 is the output follows I5. The rest of the inputs are ignored. They don't matter. So there, if you were to write out the full state table with all the columns, there would be a lot of X's indicating don't care. So, but that would be a very large matrix. So you can abbreviate it like this. Everybody have a good handle on decoders and multiplexers? And pretty basic logic circuits. Very common. You'll see them in lots of different places. Decoders can come in 1 to 2, 2 to 4, 3 to 8, 4 to 16. I haven't seen any larger than 4 to 16, but but they come in powers of 2, 1 to 2, 2 to 4, 3 to 8, 4 to 16. So multiplexers again come in different flavors as well. 1 of 2, or 2 to 1, 4 to 1, 8 to 1, 16 to 1, that sort of thing. For the sake of completeness, sometimes these are called demuxers or demultiplexers, because it kind of separates out into multiple lines your inputs. So yeah. I believe we'll get into next session. Well, we got time. Yeah, we'll go ahead and do adders. The adder functions. Actually doing math with binary numbers in hardware. Now, when you add 2 binary numbers together, 2 binary digits, you say you have A and B, you have the sum and the carry as an output. So what's and this is as easy as simple addition, 1 and 1. What's 0 plus 0? 0. 0 plus 1? 1. 0, 1. 1 plus 0? 1. 1 plus 1? 1, 0, and carry the 1. Exactly. So that's where your carry bit comes in. Now, you can see that this is basically 2 logic functions working together. This logic function and this logic function. What is the function for the sum? What function does that have relative to A and B? Anybody recognize that function? It's the exclusive OR. It's high if either bit or the other bit is high, but low if they're the same. That's the exclusive OR operation. Now this one, the carry, what operation is that? This one's easier. You've been dealing with it all semester long in lab and here. What is that function for the carry? AND gate. There it is. So you have your half adder. That's a half adder. It does, it adds two binary digits together to get a sum and a carry. But what if you have multiple bits going together? You need to add the carry to the next bit's addition, right? So you have what's called a full adder, which is two half adders. You have, let's go ahead and do the CN, A, B, C out, and sum. And we'll do the state table real quick. All right, so you're adding 3 bits together. So the total is still going to be 2 bits because adding 3 bits together, the largest number you can get is 3, right? 1 plus 1 plus 1 is 3. So that can be represented by 2 bits. So you have 0 plus 0 plus 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Again, from over here is 1, 0. 1, 0, 0 is back to 1. 1, 0, 1. 1, 1, 0. And 1, 1, 1. So that's your state table for the full adder. And put that up here. All right. So how do you link up 2 half adders together to make a full adder? Well, you have your A and B and your CN. You add your A and B together. Add your CN to that. That's your sum. And then you have your carry. So you can see that this is a one adder here, and one adder here, or half adder, I should say, one half adder, and it's two half adders linked together. And that will give you the function here. So, and feel free to trace the, copy down the schematic for the full adder and trace through and see that the sum and carry do follow this state table with all 8 inputs. Now, fortunately, you don't have to draw this every time you want to do a full adder or a half adder. Schematics often use blocks where you have and you can, if you're doing a large complex schematic, you can use the block diagrams instead of having to draw out, you know, five gates for each full adder that you're putting into the circuit. You can draw a block diagram, and other engineers will know what you mean. So, but they are implemented with an XOR gate and an AND gate. And in the case of the full adder, an additional OR gate. Now, I'm going to stop here because the next step is to make what's called a ripple adder, which can also be used for subtraction as well. So that's a little bit more involved. I don't think we have time to get into all that today, but please work on the homework. It'll be due next Friday. Yes, next Friday. I'm sorry, next Thursday. We have we're Tuesday, Thursday here. So anyway, have a good day. See you on Tuesday.